In the 30s, Genzen was able to prove the consistency of arithmetics by expanding one of the standard axioms of piano arithmetics, the induction axiom. And could you tell us well, what the induction axiom does, and what the result was, and how is it not obviously in contrast with Gödel's result?
Right. Well, take the standard induction postulate for a start. You can phrase it in different ways, but one way of phrasing it is this. If something is true of naught, and whenever it's true of n, it's true of n plus 1, then it's true of all numbers. If it's true of naught, it's true of 1, so it's true of 1. If it's true of 1, it's true of 2, and so it's true of 2, and so on all the way up. Or you can phrase it equivalently by saying, look, if it's true of naught and it's true of all numbers up to n, it's true of n plus 1. Oh, it's sort of equivalent. All right. Now, that induction principle deals with ordinary numbers, 0, 1, 2, 3, 4, 5, and so on. But we now know that there are lots more numbers beyond the natural numbers. So this takes us into set theory a bit. In set theory, there are more than the standard finite numbers. There are lots of infinite numbers. Lots and lots and lots of infinite numbers. Okay. So in particular, after 0, 1, 2, 3, 4, 5, etc., comes another one. And set theorists call this omega. And then there's omega plus 1, omega plus 2, blah, blah, blah. 2 lots of omega, 2 lots of omega plus 1, 3 lots of omega, blah, blah, blah. Omega lots of omega.
And these are numbers that we know exist only on the basis of the fact that they are a model of the axioms, right?
Well, you can deduce that these things exist. I mean, Cantor was the first person to, in some sense, establish the existence of these things. He didn't have an axiomatic set theory at the time, but he showed how you can deal with infinite numbers like this. And you can certainly establish all these things in standard contemporary set theories. So, you know, there's the first infinite number is omega, and you can have omega squared, omega cubed, omega to the fourth, blah, blah, blah. And you've only just started, Jesus Christ. I mean, you know, all these numbers are very, very small. They're all the same size as omega, you know, but then in ordinals, these infinite numbers get much, much larger than that. All right. So you've got all these other numbers. Now, there's a principle of induction which applies not just to natural numbers, but applies to infinite numbers. Okay. And you just generalize this to do with infinite numbers. And the easiest way to generalize it is to say, well, look, if it's true of naught and it's true of every ordinal less than this, it's true of this. Okay. So that's a bit like the finite version. If it's true of naught and if it's true of all numbers up to n, then it's true of n. So this is the same, except that you are dealing with infinite numbers, and the principle of induction says, well, you know, if it's true of naught, and it's true of all numbers below this ordinal, then it's true of this ordinal too. And the principle of induction says, well, hey, if you got that the case, then it's true of all ordinals. So that's the transfinite principle of induction. Now, what Genson showed is that you can prove the consistency of arithmetic, first order arithmetic, if you're allowed to use transfinite induction. You don't need it in full generality. What you need is transfinite induction up to a certain level in the hierarchy of ordinals. Namely, you need it up to this transfinite ordinal that's sometimes called epsilon naught. And epsilon naught is this. Consider the following sequence of ordinals: omega, omega to the omega, omega to the omega to the omega, omega to the omega to the omega, etc., etc., etc. Then epsilon naught is the least ordinal greater than all those guys. It's still very, very small. And what Genson showed is if you allow yourself transfinite induction, not for all ordinals, but just up to epsilon naught, you can prove the consistency of arithmetic. Because you can't prove this in arithmetic itself, because there's no way you can talk about ordinals that are as large as epsilon naught.
So in a sense, this proof is from outside piano arithmetics, and that's why it escapes the Gödel prohibition, let's say.
That's right. You know, in some sense, it's finite. Well, you know, it's not. Well, it's not in one sense, obviously, because you're dealing with quantifiers over not just the natural numbers, but you know, lots of ordinals. But in another sense, it's finite in the sense that, you know, transfinite induction looks pretty safe. I mean, you know, you don't have to do any sort of heavy-duty set theory. You just have to be able to add one and then collect up sometimes. That's all you need. All right, so maybe that's not finite tree, but it's pretty weak as a bit of reasoning goes.
Mm-hmm. Well, what happens if you replace the standard induction axiom with the transfinite induction axiom? What kind of system do you get, and what's its Gödel problem?
Well, okay. I mean, to even formulate transfinite induction, you've got to be able to talk about ordinals, at least some of them. So you need a certain amount of set theory. And you can apply the Gödel result to these in a slightly more complicated way to show that to prove the consistency of some theory of sets, you need to do transfinite induction up to some ordinal that can't be captured in the system. So if you've got a bit of set theory which allows you to do transfinite induction up to epsilon naught, you can't prove it by transfinite induction up to epsilon naught. You'll have to have a bigger ordinal. So there's this game of tail catching that goes on. You know, yeah, you can prove consistency if you've got all this extra junk, but then to prove the consistency of that plus the extra junk, you're going to have some extra junk, and so on. As long as you remain consistent. Consistency is always going to force you, in any consistency proof, to have extra junk.
But all these transfinite ordinals are themselves models of standard arithmetics, right? So how does not the standard induction axiom apply to them already without any modification of the axioms?
Well,
how could it fail to apply to them if they are just numbers in a sense? I mean, they are objects that satisfy the axiom. So as far as the axioms are concerned, they are numbers, right?
Well, they're numbers, but they're not natural numbers. So just take omega, for example. Omega is such that it's true that it's, okay, omega is greater than any natural number. Okay. Now, if you add the axiom, that there's a number greater than every natural number to arithmetic, it becomes inconsistent. So once you start to talk about transfinite ordinals, it's going to take you beyond what you can say in first order arithmetic.
But aren't chains of natural number-like sets models of standard arithmetics? I mean, isn't that there exists a number that is greater of all the others? Isn't that already part of the standard, non-standard models of arithmetic?
Okay. Yeah, look, non-standard models of arithmetic are quite different. They don't use ordinals. They have a quite different structure. Okay, we can talk about that if you like, but non-standard models of arithmetic have nothing to do with transfinite ordinals. But there is a sort of tricky issue here, because some transfinite ordinals you can sort of talk about with the natural numbers. So just think about omega plus omega. So this is all the natural numbers plus all the natural numbers again. Now that's a kind of structure, and you can sort of talk a bit about that structure in natural numbers. So it's true that you haven't got another set of natural numbers to play with, but just consider the ordering of natural numbers, which says 0, 2, 4, 6, 8, blah, blah, blah. Then when you've done all those, we'll have 1, 3, 5, 7, 9, blah, blah, blah. Okay, so that's a perfectly well-defined sequence of numbers. And that has the same structure as the transfinite ordinal, omega plus omega. So there's a sense in which you can say some things about transfinite ordinals in arithmetic, but this is going to give out at some stage. What the Genson proof shows is it's going to give out. You can't get to epsilon naught that way. So
okay.
I was a bit asked to say that you can't sort of express things about transfinite ordinals in arithmetic. You can to a certain extent, but never enough to prove the consistency of the arithmetic.
Mm-hmm. Okay, so you have a great week.
And you, stay safe. I said something which was false. Let me just backtrack to that. I mean, omega is greater than all natural numbers. I said that if you add that axiom to arithmetic, you're going to get inconsistent. That's not quite true. What is true is that you can't even express that in arithmetic, because you've got no way of talking about all the natural numbers. That's the sort of famous undefinability result. So what I said about adding that axiom to arithmetic is actually not true. What's true is you can't even express a thing to damn well add it in the first place. So I'm sure I've said many false things in these discussions. However, that's one that I know that I've said that's false.
Okay. Ciao, Graham. Thank you very much.
All right. So I'll speak to you next week.
Ciao.
Okay. Ciao, Emiliano.
Ciao.